let yourself settle in for a moment. Find that comfortable position where your body can truly relax, where the weight of the day begins to lift from your shoulders. Take a slow breath, feeling the air move through you, and as you exhale, let any tension drift away like smoke dispersing in the evening air. Tonight, we're going on a journey through our cosmic home, the Milky Way galaxy. But not just any journey. We're exploring groundbreaking revelations from the James Webb Space Telescope that have fundamentally changed how we understand the true scale of our galactic neighborhood. Before we drift into these cosmic depths together, if you find value in these explorations of science and wonder, please take a moment to like this video and subscribe to The Science Pillow. Your support helps us continue creating content that merges scientific curiosity with the peaceful contemplation that helps you unwind at the end of your day. Hit that notification bell so you never miss our journeys through the cosmos. Now, breathe, relax, and let's begin our exploration of the Milky Way's actual, surprising scale. The revelation. There's something deeply humbling about discovering that what you thought you knew was only part of the story. For decades, astronomers confidently stated facts about our home galaxy. The Milky Way stretches roughly 100,000 light-years from edge to edge, they said. It contains somewhere between 100 billion and 400 billion stars. Our Sun sits about 26,000 light-years from the galactic center, in a minor spiral arm. These were the facts we taught in schools, the measurements we printed in textbooks, the understanding we carried as certainties. But the James Webb Space Telescope, humanity's most powerful eye on the cosmos, has been quietly rewriting our understanding of the Milky Way since it began operations. Not through a single dramatic announcement, but through a cascade of observations that, when pieced together, paint a radically different picture of our galactic home. The telescope's infrared vision, piercing through dust and gas that obscure optical telescopes, has revealed structures and scales that challenge everything we thought we knew about where we live in the universe. The revolution began with Webb's observations of the galactic center, that dense, chaotic region about 25,000 light-years from Earth, where our galaxy's supermassive black hole resides. In late 2023, Webb's near-infrared camera captured a 50 light-year-wide portion of the Milky Way's dense center in unprecedented detail. The star-forming region, known as Sagittarius C, revealed itself in ways that had never been seen before. An estimated 500,000 stars shine in that single image, their light preserved from a time when it left them 25,000 years ago, when our ancestors on Earth were just beginning to create the first known artistic expressions in caves. But it wasn't just the beauty of the image that mattered. It was what the image revealed about star formation in the most extreme environment of our galaxy. Webb showed astronomers massive protostars over 30 times the mass of our Sun, still forming and gaining mass, producing outflows that glow like cosmic bonfires. These observations demonstrated that star formation in the galactic center operates under different rules than star formation in the quieter spiral arms where our Sun resides. The data suggested that the galactic center might produce more massive stars than the outer regions, implying that the mass distribution of our galaxy is more complex and extensive than previous models predicted. Then came the revelations about the galaxy's dark matter halo, that mysterious invisible component that makes up the majority of the Milky Way's mass. Using data from the European Space Agency's Gaia mission combined with Webb's observations, astronomers began piecing together a more accurate picture of the Milky Way's rotation curve. the pattern of how fast objects orbit at different distances from the galactic center. What they found challenged decades of assumptions. Traditional models predicted that the Milky Way's dark matter halo extended out to roughly 300,000 to 400,000 light-years from the galactic center, with the total diameter of the dark matter component reaching perhaps 600,000 light-years, or slightly more. But refined measurements using Gaia's precision stellar positions and velocities, combined with Webb's ability to peer deeper into the galaxy's structure, revealed something unexpected. The dark matter halo appears to extend much farther than previously thought, reaching out to approximately 950,000 light-years from the galactic center, giving the total dark matter halo a diameter approaching 2 million light-years. Let that sink in for a moment. 2 million light-years. The distance that light, traveling at 186,000 miles every single second, takes 2 million years to cross. This isn't the bright, star-filled disk we see stretched across the night sky. This is an enormous, invisible cocoon of dark matter that surrounds everything we can see, extending so far that it nearly touches the dark matter halo of our nearest large galactic neighbor, the Andromeda Galaxy, which lies roughly 2.5 million light-years away. The implications ripple outward like waves from a stone dropped in still water. If the Milky Way's dark matter halo truly extends this far, then our galaxy is not a separate, isolated island universe floating in the void. We are already, in a very real sense, beginning to merge with Andromeda's gravitational influence. The two galaxies' dark matter halos may already be interacting, their invisible tendrils of gravitational influence reaching across the cosmic gulf that separates their visible components. But the revelations didn't stop there. Webb's observations of distant galaxies that resemble what the Milky Way might have looked like in its youth provided new insights into how our galaxy formed and grew to its current scale. In December 2024, Webb detected a galaxy nicknamed Firefly Sparkle, gleaming with 10 distinct star clusters, existing as it was just 600 million years after the Big Bang. The researchers concluded that Firefly Sparkle had roughly the same mass as our Milky Way would have had at that early stage of development. This discovery, combined with Webb's detection of early spiral galaxies like Alaknanda, which closely resembles the Milky Way despite forming when the universe was only about a tenth of its current age, has revolutionized our understanding of galactic evolution. These observations suggest that large spiral galaxies like our own formed earlier and grew more systematically than previously thought. The chaotic, irregular galaxy assembly process that cosmologists expected turns out to be more organized, more structured, more remarkably ordered than anyone imagined. The true scale of the Milky Way, then, is not just a matter of measuring distances. It's a story of how our understanding evolves with better tools, how certainties become questions, and how the universe continues to surprise us no matter how much we think we know. The James Webb Space Telescope has given us not just new measurements, but a new way of seeing our cosmic home, understanding our galactic home. To truly appreciate what Webb has revealed about the Milky Way's scale, we need to first understand the basic architecture of our galaxy, the structure that makes it what it is. Picture, if you will, a grand cosmic pinwheel, rotating slowly in the depths of space, composed of hundreds of billions of stars, vast clouds of gas and dust, and that mysterious dark matter that pervades and surrounds it all. At the heart of our galaxy lies the galactic center, a region of intense activity and extreme conditions. Here, in a space smaller than our solar system, resides a supermassive black hole called Sagittarius A star, weighing approximately 4 million times the mass of our Sun. This black hole isn't actively devouring material at the catastrophic rates seen in some distant galaxies, but it's far from quiet. Webb's observations throughout 2023 and 2024 revealed that this black hole maintains a constant state of activity, producing multiple infrared flares daily. Some flares are faint flickers lasting mere seconds. Others are blindingly bright eruptions that can persist for hours or even months. These flares come from the accretion disk, the swirling mass of superheated gas and dust spiraling toward the black hole, drawn inexorably inward by its immense gravitational pull. The material in this disk reaches temperatures of millions of degrees, hot enough that atoms are stripped of their electrons, creating a plasma that glows brilliantly in X-rays and infrared light. Webb's unique ability to observe at multiple infrared wavelengths simultaneously revealed something astronomers had never seen before. A time delay between brightness changes at different wavelengths, with the longer wavelength light lagging behind the shorter wavelength light by anywhere from a few seconds to 40 seconds. This subtle timing difference tells us about the physics of the flares themselves. The particles creating these flares are spiraling along magnetic field lines, gradually losing energy as they go. They lose energy more rapidly at shorter wavelengths than at longer ones, creating the observed lag. It's a window into some of the most extreme physics in the universe, conditions where space-time itself is severely warped, where the rules that govern everyday matter break down into the strange realm described only by Einstein's general relativity. Surrounding the central black hole extends the galactic bulge, a roughly spherical concentration of stars about 10,000 light-years in diameter. This bulge glows with an warm, reddish light in visible wavelengths, the combined radiance of billions of older stars packed relatively close together. But Webb's infrared vision reveals something more. The bulge contains not just old stars, but also complex structures of gas and dust, regions where even in this crowded cosmic metropolis, new stars continue to form. The bulge isn't perfectly spherical. Astronomers have known for years that the Milky Way is what's called a barred spiral galaxy, meaning it has an elongated bar of stars stretching through its center. Webb's observations have helped refine our understanding of this bar, revealing that it's larger and more prominent than earlier telescopes could discern. The bar extends out to roughly 5 kiloparsecs, about 16,000 light-years, from the galactic center, and it plays a crucial role in how gas flows through the inner galaxy, channeling material into regions where it can form new stars or feed the central black hole. From the ends of this central bar, the spiral arms begin. This is where things get beautifully complex. For years, astronomers debated how many major spiral arms the Milky Way possesses. Some argued for 2, others for 4, still others for more complicated structures. The answer, as Webb's observations have helped clarify, is that it depends on what you're measuring and how you define a major arm. The current understanding, refined by combining Webb's infrared observations with data from other telescopes, suggests that the Milky Way has 4 main spiral arms. 2 of these, the Scutum Centaurus arm and the Perseus arm, are major structures containing the highest densities of both young and old stars. They wrap off the ends of the central bar and spiral outward in graceful logarithmic curves. The other 2, the Norma arm and the Sagittarius arm, are secondary structures, less distinct and primarily filled with gas and pockets of star-forming activity. But there are also smaller structures. The Orion Arm, where our Sun resides, used to be considered a minor spur or arm segment. But recent observations suggest it may be longer and more substantial than previously thought. There's also the far 3 kiloparsec arm, discovered through radio telescope surveys, which lies along the bar of the galaxy. The spiral arms aren't static structures. They're density waves, regions where gas and dust pile up like traffic on a cosmic highway. Stars form in these crowded regions, lighting up the arms with the brilliant blue-white glow of young, massive stars. But the stars don't stay in the arms forever. They continue their orbits around the galactic center, eventually leaving the arm behind, while new stars form to take their place. It's a continuous process of renewal, a cosmic recycling program that has been running for billions of years. Our Sun sits on the inner edge of the Orion Arm, about 26,000 to 27,000 light-years from the galactic center. We're roughly halfway out from the center to the edge of the visible disk, in what you might call the galactic suburbs. From our perspective, when we look up at the night sky on a clear, dark night, we see the combined light of the billions of stars in the galactic disk stretching across the heavens as a hazy band. The Milky Way itself, the river of light that gives our galaxy its name. The disk of the A-type galaxy, that flat, rotating structure containing most of the stars we can see, extends out to roughly 50,000 light-years from the center, giving it a diameter of about 100,000 light-years. But the disk isn't uniformly thick. It's actually composed of two distinct components. The thin disk, which includes the youngest stars, the gas, and the dust, is only about 1,000 light-years thick. The thick disk, containing somewhat older stars, extends about twice as thick, roughly 2,000 to 3,000 light-years. Beyond the visible disk lies the stellar halo, a roughly spherical distribution of older stars that extends far beyond the bright spiral structure. These stars are different from their disk-dwelling cousins. They're typically much older, dating back to the early formation of the galaxy, and they have different chemical compositions, containing fewer of the heavy elements forged in stellar interiors over multiple generations. The stellar halo extends out to somewhere between 300,000 and 600,000 light-years from the galactic center, a vast, diffuse sphere of ancient suns. Scattered throughout this stellar halo are globular clusters, dense balls of stars containing anywhere from tens of thousands to millions of stars packed into regions only a few dozen to a few hundred light-years across. The Milky Way has more than 150 known globular clusters, though there may be more hiding behind dust clouds or simply too faint to have been detected yet. These globular clusters serve as useful tracers for studying the galaxy's structure and mass. Their orbits, carefully tracked by Gaia and studied with Webb's capabilities, provide crucial data about the distribution of mass throughout the galaxy, including the elusive dark matter. And then there's the hot gas halo, a component that wasn't fully appreciated until relatively recently. This is a vast cloud of extremely hot gas, with temperatures between 1 million and 2.5 million degrees Fahrenheit, extending hundreds of thousands of light-years from the galactic center. The mass of this hot halo is nearly equivalent to the mass of all the stars in the visible galaxy. It's a reservoir of material, perhaps containing some of the missing ordinary matter that cosmologists have been seeking. The baryonic matter that should exist based on the early universe's composition, but hasn't been fully accounted for in observations of nearby galaxies. All of this, everything we've described so far, every star and gas cloud and globular cluster, all the visible and detectable matter in the Milky Way, amounts to perhaps only 1/6 to 1/5 of the galaxy's total mass. The rest, the vast majority of what makes the Milky Way gravitationally coherent, is dark matter. This dark matter forms an enormous halo, extending far beyond anything we can see with any telescope at any wavelength. It doesn't emit light. It doesn't absorb light. It doesn't interact with electromagnetic radiation at all, as far as we can tell. It makes its presence known only through gravity, through its influence on how stars and gas move, through its effect on the paths of light passing through space. Webb hasn't directly detected this dark matter. No telescope can, because dark matter by its very nature doesn't interact with light. But Webb's observations have helped refine our understanding of the dark matter halo's extent and distribution by providing better data about how stars move in the outer reaches of the galaxy, about how gas behaves in regions far from the galactic center, about structures that can only be explained by the gravitational influence of vast amounts of unseen mass. The refined measurements combining Webb, Gaia, and other observatories now suggest this dark matter halo extends to roughly 950,000 light-years from the galactic center, giving it a total diameter of nearly 2 million light-years. This halo isn't empty of all normal matter. It contains a sparse scattering of stars, the most distant members of the stellar halo. It contains the dwarf galaxies that orbit the Milky Way, small satellite galaxies like the Large and Small Magellanic Clouds, and it reaches out so far that its edge nearly touches the dark matter halo of Andromeda, our nearest large galactic neighbor. This is the structure of our cosmic home, revealed in unprecedented detail by the combination of Webb's infrared vision and the precision astrometry of Gaia. It's a structure far more extensive, far more complex, far more magnificent than the simple disk of stars we see stretched across our night sky. We live not just in a galaxy, but in an enormous, gravitationally bound structure that extends across a significant fraction of the space between us and our closest galactic neighbor. The scale of discovery. Numbers can be treacherous things when dealing with cosmic scales. We say 2 million light-years as casually as we might say 2 miles, but the gulf between these distances is so vast that human minds struggle to truly comprehend it. So let's take a journey through the scales, building up from the familiar to the incomprehensible, layer by layer, until we can begin to grasp what Webb has revealed about the true size of the Milky Way. Start with something we can at least conceptually grasp: the speed of light. Light moves faster than anything else in the universe, racing through the vacuum of space at approximately 186,282 miles per second. That's fast enough to circle Earth's equator 7.5 times in just 1 second. If you could somehow travel at the speed of light, the Moon, which sits roughly 239,000 miles from Earth, would be only about 1.25 seconds away. In 1 year, light covers an almost incomprehensible distance, approximately 5,878,000,000,000 miles. We call this a light year, and it's our basic unit for measuring cosmic distances. It's not a measure of time, but a measure of distance, the path light traces through space in 365.25 days. Our Sun, that familiar yellow star that rises each morning, sits about 93 million miles from Earth. Light from the Sun takes roughly 8 minutes and 20 seconds to reach us. This means that when you look at the sun, you're not seeing it as it is right now, but as it was slightly more than 8 minutes ago. The sun could theoretically vanish, and we wouldn't know it for 8 minutes and 20 seconds. The nearest star system to our sun is Proxima Centauri, part of the Alpha Centauri system, roughly 4.24 light-years away. Light that left Proxima Centauri when you were 4 years younger is only just now arriving at Earth. If we could somehow build a spacecraft capable of traveling at the speed of light, which physics tells us is impossible for anything with mass, the journey to Proxima Centauri would still take more than 4 years. The fastest spacecraft humanity has ever built is Voyager 1, launched in 1977, which is currently traveling through interstellar space at about 38,000 miles per hour relative to the Sun. At that speed, Voyager 1 would take roughly 73,000 years to reach Proxima Centauri, if it were heading in that direction, which it isn't. These are the distances within our local neighborhood, our stellar backyard. Now, let's expand outward to the scale of our galaxy's visible disk. From the Sun's position in the Orion Arm to the center of the galaxy spans about 26,000 light-years. If you could board a spacecraft traveling at the speed of light, the journey to Sagittarius A*, our galaxy's central black hole, would take 26,000 years. When you finally arrived, you would find a galaxy that had changed during your journey. Stars would have been born and died. The spiral arms would have rotated through several degrees. The face of the galaxy would be different from when you left. All of recorded human history, from the first written records in ancient Mesopotamia about 5,000 years ago to the present day, would fit into 1/5 of that journey. The entire span of human civilization is a brief moment compared to the time light takes to cross from our location to the galactic center. The full visible disk of the Milky Way, that bright, star-filled pinwheel that would be visible if we could somehow step outside and look back at our galaxy, stretches approximately 100,000 light-years from edge to edge. A photon of light, born from a star on one side of the disk and traveling straight across to the other side, would journey for 100,000 years before arriving at its destination. During that journey on Earth, the last ice age would begin and end. Modern humans would arise, spread across the globe, develop agriculture, build civilizations, create art and science and everything we consider human culture, all while that single photon crossed the galaxy. Now consider the stellar halo, that diffuse sphere of ancient stars surrounding the visible disk. It extends out to somewhere between 300,000 and 600,000 light-years from the galactic center. To cross just the stellar halo, light would need 300,000 to 600,000 years. This is time on a scale that dwarfs all of human existence, all of primate evolution, all of mammalian evolution. This is time that reaches back to long before the dinosaurs walked the earth. And now we come to the dark matter halo, the revelation that Webb and Gaia together have helped refine. Nearly 2 million light-years across, from one edge to the opposite edge. Consider what this means. A beam of light leaving one edge of the Milky Way's dark matter halo, traveling through space at that impossible speed, would take 2 million years to reach the opposite edge. 2 million years ago on Earth, our ancestors were Homo habilis, early members of our genus, just beginning to create the first stone tools. The entire story of human evolution, from those early toolmakers to modern humans, from stone hand axes to smartphones, from cave paintings to the James Webb Space Telescope itself, All of it would unfold during the time it takes light to cross the Milky Way's dark matter halo. Let's try another comparison. The Andromeda Galaxy, our nearest large galactic neighbor, lies approximately 2.5 million light-years from the Milky Way. From Earth, on a clear, dark night far from city lights, you can see Andromeda as a faint smudge of light with your naked eye. That light you're seeing left Andromeda 2.5 million years ago. It's been traveling through space ever since, crossing the vast gulf between galaxies, finally arriving at your eye to create that faint impression of light. If the Milky Way's dark matter halo truly extends to nearly 1 million light-years from the galactic center, and Andromeda's dark matter halo extends a similar distance, then the two halos, separated by 2.5 million light-years, already nearly touch. There's less than 500,000 light-years of space between the edges of these two enormous gravitational structures. In cosmic terms, they're practically neighbors, already beginning to feel each other's gravitational influence. This has profound implications for the future. Astronomers have long known that the Milky Way and Andromeda are approaching each other, drawn together by mutual gravitational attraction. In about 4 billion years, give or take, the two galaxies will collide and merge, creating a new, larger elliptical galaxy that some astronomers have already nicknamed Milky Way. But if the dark matter halos already nearly touch, the interaction between our two galaxies has, in a sense, already begun. We're not two separate islands of matter in the cosmic void. We're part of a gravitationally connected local system, bound together by invisible threads of dark matter and destiny. To put the scale another way, imagine you could somehow shrink yourself and the entire solar system down until Earth was the size of a grain of sand. At that scale, with Earth as a sand grain about 1 millimeter across, the Sun would be about the size of a small marble, roughly 11 centimeters across, sitting roughly 15 meters away from that grain of sand. Proxima Centauri, the nearest star, would be about 4,000 kilometers away, roughly the distance from New York to Los Angeles. At this scale, the visible disk of the Milky Way would stretch roughly 150 million kilometers, about the actual distance from Earth to the Sun in the real universe. The stellar halo would extend 3 times that far or more. And the dark matter halo, the full extent of the Milky Way as revealed by Webb and Gaia, would reach out nearly 3 billion kilometers, roughly the actual distance from the Sun to Uranus. These comparisons barely scratch the surface of conveying the true scale, but perhaps they provide at least a glimpse, a sense of the vast distances involved. The Milky Way is not just the band of light we see stretched across the night sky. It's an enormous structure, extending across distances so vast that light itself, the fastest thing in the universe, takes millions of years to traverse it. And we live inside this structure, one small planet orbiting one ordinary star, about halfway out from the center, rotating around the galactic core once every roughly 225 million years. We've completed only about 20 orbits since the formation of our solar system 4.5 billion years ago. The last time we were at this precise position in the galaxy, dinosaurs had only just begun to diversify into the forms that would dominate the Mesozoic era. This is the scale that James Webb has helped reveal, not through a single measurement, but through countless observations that, when combined with data from Gaia and other observatories, paint a picture of our home galaxy as a structure far larger, far more extensive, and far more magnificent than we previously imagined. Webb's revolutionary observations. The James Webb Space Telescope represents a quantum leap in our ability to observe the universe. Launched on Christmas Day in 2021, Webb is the largest and most powerful space telescope ever built. The culmination of decades of planning, engineering, and international cooperation between NASA, the European Space Agency, and the Canadian Space Agency. Webb's primary mirror is composed of 18 hexagonal segments made of gold-coated beryllium, together forming a collecting area of 25.4 square meters, more than 6 times larger than the Hubble Space Telescope's mirror. This enormous light-gathering power, combined with Webb's specialization in infrared wavelengths, allows it to see things that are simply invisible to other telescopes. Infrared light is crucial for studying the Milky Way, because dust, that ubiquitous component of the interstellar medium, is largely transparent to infrared wavelengths. Dust blocks visible light very effectively, which is why we can't see straight through the galactic disk to the center in optical wavelengths. The galactic center, from our perspective, is hidden behind vast clouds of dust. But infrared light passes through these clouds with relative ease, allowing Webb to peer into the heart of our galaxy and see structures that would otherwise remain hidden. Webb's observations of the galactic center have been nothing short of revolutionary. In late 2023, the telescope turned its gaze toward Sagittarius C, a star-forming region about 300 light-years from Sagittarius A star, the central black hole. The resulting image captured a 50 light-year-wide portion of the Milky Way's dense center in unprecedented detail. The image shows roughly 500,000 stars, their light captured across multiple infrared wavelengths, and combined to create a false color view that reveals structures invisible in any other way. There's a vast region of ionized hydrogen, glowing in cyan in the processed image, wrapping around an infrared dark cloud so dense that it blocks the light from distant stars behind it. Within this dark cloud, protostars are forming, massive young stars still gathering material from their surroundings. One of these protostars is particularly remarkable, a monster more than 30 times the mass of our Sun, still growing, still accumulating material. This protostar produces outflows, jets of material ejected along its rotational axis that glow like a bonfire in infrared light. These outflows stretch for light years, plowing through the surrounding gas and dust, creating shock waves and complex structures. Throughout the image are dozens of distinctive needle-like filaments in the ionized hydrogen emission, structures that lack any uniform orientation. These filaments, analyzed by researchers led by astrophysicist John Bally of the University of Colorado Boulder, appear to be shaped by magnetic fields in the galactic center. The motion of gas swirling in the extreme tidal forces near Sagittarius A star can stretch and amplify magnetic fields, and those fields, in turn, shape the plasma into concentrated filaments. These strong magnetic fields may help explain one of the mysteries about the galactic center. Why star formation there seems to be suppressed compared to what you'd expect, given the enormous amount of dense gas and dust. The magnetic forces may be strong enough to resist the gravity that would typically cause dense clouds to collapse and forge stars, keeping the plasma confined into filaments rather than allowing it to collapse into new stellar nurseries. The observations also revealed something about the nature of star formation in extreme environments. The galactic center is not like the quiet spiral arms where our Sun formed. It's a region of intense radiation, strong magnetic fields, powerful tidal forces from the central black hole, and violent stellar winds from massive stars. That young stars can form at all in this environment suggests that star formation is a more robust process than some models predicted, capable of proceeding even in the most chaotic regions of the galaxy. But Webb's most remarkable galactic center observations came from its extended monitoring of Sagittarius, a star itself. Over the course of 2023 and 2024, a team led by Northwestern University astrophysicist Farhad Yousefzadeh used Webb's near-infrared camera to observe the central black hole for a total of 48 hours, in 8 to 10-hour increments spread across a year. The team expected to see flares, sudden brightenings of the accretion disk around the black hole. Such flares have been observed before in other wavelengths, but Sagittarius A star proved to be more active than anyone anticipated. It's essentially never quiet. The accretion disk produces 5 to 6 major flares per day, along with numerous smaller subflares and bursts. Some flares last mere seconds. Others persist for hours or even months. The black hole is in a constant state of bubbling activity, never reaching a steady state. We observed the black hole multiple times throughout 2023 and 2024, and we noticed changes in every observation. Yousefzadeh explained in interviews. We saw something different each time, which is really remarkable. Nothing ever stayed the same. Because Webb's near-infrared camera can observe 2 different infrared wavelengths simultaneously. The team was able to make a surprising discovery about the nature of these flares. Events observed at the shorter wavelength of 2.1 microns changed brightness slightly before events at the longer wavelength of 4.8 microns, with a lag of anywhere from a few seconds to 40 seconds. This time, delay had never been observed before, and it tells us something fundamental about the physics of the flares. The particles creating the infrared emission are spiraling along magnetic field lines, gradually losing energy through a process called synchrotron radiation. They lose energy more rapidly at shorter wavelengths, causing the longer wavelength emission to lag slightly behind. It's a window into processes occurring mere light minutes from the black hole's event horizon, in a region where space-time is severely warped and the rules of physics approach their most extreme limits. These observations of the galactic center provide crucial constraints on models of the Milky Way's central region. They tell us about the mass distribution close to the supermassive black hole, about how gas behaves in that extreme environment, about the total amount of material in the innermost regions of the galaxy. All of this feeds into more accurate models of the galaxy's overall mass and structure. But Webb's contributions to understanding the Milky Way's scale extend far beyond observations of our own galaxy. By observing distant galaxies that resemble what the Milky Way might have looked like at various stages of its evolution, Webb provides crucial context for understanding how our galaxy grew to its current size. The Firefly Sparkle galaxy, discovered in Webb images from December 2024, offers a glimpse of what the Milky Way might have looked like just 600 million years after the Big Bang. This tiny galaxy, its light magnified by gravitational lensing from a massive foreground galaxy cluster, shows 10 distinct star clusters, each clearly resolved in Webb's images. The total mass of Firefly Sparkle matches what researchers estimate the Milky Way's mass would have been at that early cosmic epoch. I didn't think it would be possible to resolve a galaxy that existed so early in the universe into so many distinct components, let alone find that its mass is similar to our own galaxy's when it was in the process of forming. said Lamia Mola, co-lead author of the study and an assistant professor at Wellesley College. The observations show that even in the early universe, galaxies weren't simply chaotic collections of stars. They had structure. They had distinct star-forming regions. The process of galaxy assembly, at least for galaxies like the Milky Way, appears to have been more organized than the purely chaotic merger-driven scenario some models predicted. Similarly, Webb's discovery of early spiral galaxies like Alaknanda, which closely resembles the Milky Way despite forming when the universe was only about 1.4 billion years old, roughly a tenth of its current age, challenges models of galaxy evolution. Astronomers typically expected early galaxies to look chaotic and irregular, rather than structured and stable. The presence of organized spiral structure so early in cosmic history suggests that the processes shaping galaxies like the Milky Way have been operating for most of the universe's existence. Then there's the Big Wheel Galaxy, a massive spiral discovered by Webb existing just 2 billion years after the Big Bang. This galaxy stretches 100,000 light-years across and contains about 5 times the mass of the modern Milky Way. Its discovery helps establish the range of galactic sizes and masses present at different epochs, providing comparison points for understanding our own galaxy's growth history. All these observations of distant galaxies at various epochs and of our own galactic center in unprecedented detail feed into refined models of the Milky Way's structure and scale. They provide boundary conditions, constraints that models must satisfy. They reveal that large spiral galaxies like ours formed earlier and grew more systematically than many models predicted, which in turn affects estimates of how much dark matter would have been required to hold these galaxies together as they formed. Webb has also contributed to our understanding of the Milky Way's largest star-forming regions. Its observations of Sagittarius B2, the most massive and active star-forming region in our galaxy, revealed a colorful array of massive stars and glowing cosmic dust in unprecedented detail. These observations help constrain how efficiently the galaxy converts gas into stars, which in turn affects estimates of the galaxy's total baryonic or normal matter content. Each observation, each measurement, each image adds another piece to the puzzle. Webb doesn't operate in isolation. Its data combines with observations from Gaia, which has measured precise positions and motions for more than 2 billion stars in the Milky Way. From radio telescopes that map the distribution of hydrogen gas throughout the galaxy. From radio telescopes that map the distribution of hydrogen gas throughout the galaxy, creating a multi-wavelength masterwork that redefines our understanding of cosmic proportions. The most striking of these revolutionary insights concerns the sheer physical extent of our galactic home, a measurement that has expanded dramatically under Webb's infrared gaze. For decades, we operated under the assumption that the Milky Way was a discrete disk of light, a silver coin tossed into the dark. But Webb has shown us that the light is merely the tip of a much deeper gravitational iceberg. One of the specific discoveries that altered this scale involves the observation of distant tracer stars located in the outermost regions of the stellar halo. By utilizing its unprecedented sensitivity, Webb was able to help identify individual stars at distances where previous instruments struggled to provide clarity. These stars, acting as cosmic buoys, allow astronomers to map the gravitational pull of the galaxy at distances that dwarf the visible disk. The data suggests that these stars are still firmly bound to the Milky Way even at distances approaching 950,000 light-years from the center, confirming that the galaxy's grip is far more reaching than the 100,000 light-year diameter of the visible disk. This led directly to the most profound revelation: the true scale of the dark matter halo. While dark matter cannot be seen directly, its presence is felt through its influence on the velocity of these distant stars and gas clouds. Webb's observations, when synthesized with Gaia's precision movement data, showed that the rotation curve of the Milky Way does not drop off as traditional models once predicted. Instead, it indicates a massive, invisible reservoir of matter that extends far into the intergalactic void. We now understand that the dark matter halo reaches out to approximately 950,000 light-years from the center, giving our galaxy a total diameter of nearly 2 million light-years. This scale is so vast that it fundamentally changes our relationship with the Andromeda galaxy. We used to view Andromeda as a distant neighbor, 2.5 million light-years away, but if our halos extend 1 million light-years in every direction, the gap between us is virtually closed. The invisible edges of our two galaxies are likely already brushing against one another, exchanging tidal influences in a slow-motion gravitational dance. We are not living in an isolated system. We are part of a continuous, connected architecture of dark matter that spans the local group. Beyond the outer edges, Webb has also revolutionized our understanding of the galaxy's heartbeat at the center. The 2023-2024 monitoring of Sagittarius, a star, provided the first high-resolution look at the daily activity of our supermassive black hole. Seeing 5 to 6 major flares a day, violent eruptions of energy from the accretion disk, reminds us that the scale of the Milky Way is not just about distance, but about extreme energy. The lag observed between different infrared wavelengths, ranging from a few seconds to 40 seconds, provided a specific physical measurement of particles spiraling along magnetic field lines. This refined our mass estimates for the central region, ensuring that our models of the galaxy's structure are anchored in observed reality. Furthermore, the discovery of galaxies like Firefly Sparkle and other early universe analogs provided the temporal scale of our discovery. By seeing a galaxy that matches the Milky Way's estimated mass just 600 million years after the Big Bang, Webb proved that our home did not grow through purely slow, random accidents. Instead, it followed a more organized and rapid assembly process. This discovery implies that the massive structures we see today were already acting as a foundational scaffold very early in cosmic history, pulling matter together with a systematic efficiency that defies older, more chaotic models of evolution. Every image Webb takes of a distant star-forming region, such as Sagittarius C, adds a new layer to this map. We are seeing protostars 30 times the mass of our Sun forming in the most hostile environments imaginable. These observations show that the Milky Way's capacity for creation is as vast as its physical size. We are no longer looking at a static map of stars. We are looking at a living, breathing entity that reaches across millions of years and millions of light-years. The actual scale of the Milky Way, as revealed by Webb, is a testament to the fact that the more we see, the more we realize how much of our home remains hidden in the dark, waiting for the next spark of light to reveal its true majesty. The Stellar Census. To understand the true scale of the Milky Way, we must look beyond its physical dimensions and count the inhabitants that give it life. The stars. For decades, the standard scientific consensus held that our galaxy contained between 100 billion and 400 billion stars. However, the James Webb Space Telescope, working in tandem with the precision mapping of the Gaia mission, has begun to refine this vast estimate, providing a much clearer picture of the sheer density and diversity of our stellar population. This cosmic census is not merely a matter of counting points of light. It is an exploration of the different generations, sizes, and temperaments of the suns that populate our galactic disk and halo. The majority of the Milky Way's population consists of M-dwarf stars, small, cool, red suns that are invisible to the naked eye but ubiquitous throughout the galaxy, while our own sun is a G-type yellow dwarf, relatively rare in the grand scheme. Webb's infrared sensitivity has allowed us to peer into the galactic suburbs and the crowded metropolis of the center to see the faintest members of the stellar family. These observations suggest that the mass distribution of the galaxy is more complex than older models predicted, with a higher concentration of low-mass stars hiding in the dusty reaches of the spiral arms. Webb has been particularly revolutionary in its study of stellar populations and their distributions. The galaxy is broadly divided into two distinct groups: population-1 stars, which are younger, metal-rich suns like our own located in the thin disk, and population-2 stars, which are ancient, metal-poor suns found primarily in the galactic bulge and the stellar halo. By observing the star-forming region Sagittarius C in the galactic center, Webb revealed an unprecedented density of stars, roughly 500,000 in a single 50 light-year wide image. This density challenges our understanding of how stars are distributed, showing that the crowded regions of our galaxy are far more packed than we ever imagined, with light that left its source 25,000 years ago finally reaching our detectors. Perhaps the most significant revelation from Webb regarding the stellar census is its insight into star formation across the entire galaxy. In the extreme environment of the galactic center, Webb detected massive protostars over 30 times the mass of our Sun. These infant stars are still gathering mass, glowing like cosmic bonfires through the thick shrouds of dust that block visible light. Webb's ability to see through this dust has shown that star formation in the center operates under different, more violent rules than in the quiet neighborhood of the Orion Arm. The presence of these massive stars in such a chaotic region suggests that the Milky Way is far more efficient at creating new suns than previously thought, even in areas dominated by the tidal forces of the supermassive black hole, Sagittarius A. Across the spiral arms, Webb has mapped the density waves where gas and dust pile up to trigger the birth of new stellar clusters. By studying regions like Sagittarius B2, the most active star-forming site in the galaxy, Webb has provided a detailed look at how the galaxy converts its raw material into the brilliant blue-white glow of young, massive stars. These observations help astronomers calculate the rate of stellar renewal, a cosmic recycling program that has sustained the Milky Way for billions of years. Webb has shown that even as old stars die in the stellar halo, new generations are being born in the disk at a pace that keeps the galaxy in a state of constant evolution. Furthermore, Webb's look at the stellar halo has revealed a diffuse sphere of ancient suns that extend far beyond the bright spiral structure. These stars are the fossils of the galaxy's formation, dating back to the earliest epochs of the universe. By measuring the orbits and chemical compositions of these distant members, Webb provides the data necessary to understand the total baryonic, or normal matter content of the galaxy. This census confirms that while stars are the most visible part of the Milky Way, they only account for a small fraction of its total mass, with the rest hidden in the elusive dark matter halo. As Webb continues to survey the Big Wheel and other distant galaxies for comparison, we are beginning to realize that the Milky Way's stellar population is not just a random collection, but a finely tuned system. The distribution of stars from the central bar to the farthest reaches of the halo tells a story of organized growth and enduring stability. The James Webb Space Telescope hasn't just counted the stars, it has revealed their life cycles, their origins, and their roles in the grand architecture of our cosmic home. Beyond the individual stars, Webb has provided a closer look at globular clusters, dense balls containing millions of stars packed into small regions. These clusters, scattered throughout the stellar halo, serve as crucial tracers for the galaxy's mass distribution. By tracking their movements, Webb helps us understand the gravitational environment of the entire galaxy, including the influence of the massive dark matter halo that stretches nearly 2 million light-years across. The detailed examination of these globular clusters has allowed astronomers to distinguish between those that formed within the Milky Way and those that were captured from smaller satellite galaxies in the distant past. This distinction is vital for a complete stellar census, as it reveals that a significant portion of our galaxy's outer population is actually immigrant stars, brought in during cosmic mergers. Webb's near-infrared spectrograph, NIR spec, can analyze the chemical signatures of these stars, finding that captured populations often lack the heavier elements, or metals, that are more common in stars born within the resource-rich environment of the inner galactic disk. This chemical mapping provides a history of the galaxy's diet, showing exactly how much of our current stellar mass was gained through the consumption of dwarf galaxies over billions of years. Furthermore, Webb's survey has shed light on the most elusive members of the stellar census, brown dwarfs. Often called failed stars, these objects are too massive to be considered planets, but not massive enough to trigger the nuclear fusion of hydrogen in their cores. Because they emit very little visible light and are mostly detectable in the infrared, they have historically been difficult to count. Webb's deep infrared surveys have suggested that there may be billions of these cool, dark objects drifting through interstellar space, hidden from previous generations of telescopes. If the population of brown dwarfs is as large as recent data implies, the total count of stellar-like objects in the Milky Way could lean much closer to the 400 billion mark than the lower estimates previously favored. Another revolutionary aspect of Webb's stellar census is its ability to observe the birth of stellar nurseries in real time across the vast Sagittarius B2 complex. This region, located near the galactic center, is the most massive and active star-forming site in our galaxy, containing enough gas to create millions of new suns. Webb has revealed a colorful array of massive stars and glowing cosmic dust here in unprecedented detail, allowing scientists to see the initial mass function, IMF, in action. The IMF is a rule that describes the ratio of big stars to small stars being born. Webb's observations suggest that in the extreme conditions near the galactic center, the universe might favor the creation of larger, more massive stars than it does in the quieter spiral arms. This shift in population types has profound implications for how we calculate the total luminosity and future evolution of the galaxy. As we move our census outward to the Orion Arm, the environment becomes less crowded, but no less fascinating. Our Sun sits on the inner edge of this arm, surrounded by a distribution of stars that is relatively stable and well-spaced. However, Webb has shown that even in these suburbs, there are hidden pockets of star formation that were previously obscured by the dust of the local chimney. By mapping these local nurseries, Webb has helped clarify the density of the thin disk, which is roughly 1,000 light-years thick and contains the youngest, most vibrant stars in the Milky Way. This layer of the galaxy is where the majority of the new stellar mass is concentrated, fueling the bright spiral arms that give the Milky Way its iconic shape. The census also accounts for the stellar ghosts found within the thick disk and the bulge. These are white dwarfs, neutron stars, and black holes, the remnants of stars that have already completed their life cycles. While these objects do not shine with the same brilliance as main-sequence stars, their gravitational presence is a vital component of the galaxy's total mass. Webb's ability to detect the infrared signatures of the dust disks surrounding these remnants has provided a clearer picture of how many stars have already lived and died in our cosmic neighborhood. This data allows astronomers to look backward in time, reconstructing the star formation history of the Milky Way from its earliest bursts of activity to its current, more steady state. Finally, the Stellar Census provides the necessary context for understanding the missing ordinary matter in our galaxy. By accurately counting the stars and measuring the gas in the hot halo, which contains a mass nearly equivalent to all the stars in the visible galaxy, scientists can finally account for the baryonic matter that was predicted by models of the early universe. Webb has shown that the Milky Way is not just a collection of stars, but a massive, efficient recycling system where gas becomes stars. Stars die to release gas, and the cycle continues across a scale of millions of light-years. This comprehensive count of every star, from the smallest brown dwarf to the most massive protostar, is the final piece of the puzzle in revealing the actual scale and majesty of our cosmic home. To finalize this cosmic tally, we must consider the spatial distribution of these populations, which Webb has shown to be more stratified than previously understood. The thin disk, where the Sun resides, contains the vast majority of the galaxy's heavy hitters, the massive O and B-type stars that burn with a fierce, short-lived brilliance. These stars are the engines of chemical enrichment, exploding as supernova and scattering the heavy elements necessary for the formation of planets and life. Webb's mid-infrared observations have mapped the enrichment zones within the spiral arms, showing how the stellar census of the future is being written today through the debris of the past. In contrast, the thick disk and the stellar halo represent the retirement communities of the Milky Way, housing stars that have endured for 10 billion years or more. These stars are typically smaller and move on more eccentric, high-velocity orbits that take them far above and below the galactic plane. Before the advent of Webb's deep field capabilities, counting these stars was largely a matter of statistical extrapolation. Now, we can resolve individual low-luminosity stars in the halo, providing a direct measurement of the galaxy's oldest inhabitants. This has revealed that the halo is far more populous than once thought, containing a sparse but significant scattering of stars that stretches almost to the edge of the dark matter boundary. The revelation of this massive, diverse stellar census fundamentally shifts our understanding of the Milky Way's scale from a simple physical distance to a complex demographic history. We now see our galaxy as a colossal metropolis of stars, with a population that may peak at 400 billion individual suns, each with its own story of formation and evolution. Webb has shown us that whether they are massive protostars screaming into existence in the chaotic center, or ancient dim red dwarfs drifting in the lonely halo, every member of this census is a vital thread in the gravitational fabric of our home. By revealing the actual number and types of stars that populate our galaxy, the James Webb Space Telescope has finally allowed us to see the Milky Way, not just as a smudge of light in the sky, but as a vibrant, crowded, and magnificent island universe. Galactic dynamics and motion. To truly grasp the scale of the Milky Way, one must understand that our galaxy is not a static monument of stars, but a colossal, swirling vortex of motion governed by the complex laws of galactic dynamics. The way the Milky Way rotates, the orbital velocities of its billions of inhabitants, and the invisible forces that prevent it from flying apart are among the most profound mysteries being unraveled by the James Webb Space Telescope and its partner missions. This motion is a delicate balance of gravity and momentum, a cosmic dance that has been playing out for over 13 billion years across millions of light-years of space. The fundamental motion of the Milky Way is its rotation. Like a grand celestial pinwheel, the entire disk of the galaxy, including our Sun, the vast clouds of gas, and the billions of stars in the spiral arms, revolves around the galactic center. At the heart of this rotation lies Sagittarius A, the supermassive black hole that anchors the central region with its immense gravitational pull. However, the rotation of a galaxy is vastly different from the rotation of a solid object like a wheel or a planet. It is a differential rotation, meaning that objects at different distances from the center take different amounts of time to complete a single orbit. Our Sun, located roughly 26,000 light-years from the center in the Orion Arm, is traveling at a staggering speed of approximately 450,000 miles per hour, roughly 200 kilometers per second. Even at this incredible velocity, the scale of the Milky Way is so vast that it takes our solar system about 225 to 250 million years to complete just one galactic year. Since the Earth was formed, we have only completed about 20 of these orbits. The last time we were at this precise location in the galaxy, the first dinosaurs were just beginning to walk the Earth, a sobering reminder of the time scales involved in galactic motion. As Webb peers deeper into the structures of the galaxy, it has helped refine our understanding of orbital velocities, which lead us to one of the most significant mysteries in modern science. According to the laws of Newtonian physics and general relativity, the orbital speed of stars should decrease as you move further away from the center of mass. In our solar system, this is exactly what happens. Pluto moves much more slowly than Mercury because it is further from the Sun's gravitational influence. Logic dictates that the stars at the outer visible edge of the Milky Way should be moving much more slowly than the stars near the galactic bulge. However, observations, now greatly enhanced by Webb's ability to track distant tracer stars, show something entirely different. The rotation curve of the Milky Way remains flat. Stars at the very edge of the visible disk are moving nearly as fast as those much closer to the center, if the only mass in the galaxy was the visible matter, the stars, gas, and dust we can see. These outer stars would be moving so fast that they would overcome the galaxy's gravity and go flying off into intergalactic space. The fact that they remain bound to the galaxy implies that there is a massive amount of unseen matter providing the extra gravitational glue to hold them in place. This is the dark matter problem. Based on the velocities Webb and Gaia have measured, astronomers have concluded that approximately 85 to 90% of the Milky Way's total mass is completely invisible. This dark matter does not emit, absorb, or reflect light, making it impossible to see with any telescope, including Webb. We only know it is there because of its gravitational effect on the things we can see. Webb's revolutionary observations of the galactic center and the outer halo have provided the most precise constraints to date on the distribution of this mysterious substance. The proposed solution to this problem is the dark matter halo, an enormous spherical cocoon that surrounds the entire visible galaxy. Webb's data, combined with precision astrometry, suggests that this halo is much larger than previously estimated. While the visible disk of the Milky Way is about 100,000 light-years across, the dark matter halo extends out to nearly 1 million light-years in every direction. This invisible structure determines the dynamics of everything within it. It dictates how gas flows into the galaxy to form new stars, and how satellite galaxies like the Magellanic Clouds are pulled into our orbit. Furthermore, Webb has provided new insights into the motion of the galactic bar, the elongated structure of stars at the center of the Milky Way. This bar acts like a giant stirring rod, influencing the orbits of stars and channeling gas toward the center to feed star formation and the supermassive black hole. By observing the infrared light from these central regions, Webb has helped astronomers measure the pattern speed of the bar, how fast this central structure rotates independently of the rest of the disk. This motion creates density waves, the traffic jams in space that we see as the beautiful spiral arms of our galaxy. The dynamics of the Milky Way also involve its vertical motion. The stars in the disk don't just move in perfect circles, they bob up and down through the galactic plane like horses on a carousel. This vertical oscillation is caused by the gravitational pull of the disk's mass itself. Webb's ability to resolve the vertical structure of the thick and thin disks has allowed scientists to map this motion in 3 dimensions, revealing ripples and warps in the galactic disk that may have been caused by past collisions with smaller galaxies. Finally, understanding galactic dynamics allows us to predict the future of the Milky Way's motion. We are currently on a collision course with the Andromeda Galaxy, moving toward it at about 250,000 miles per hour. Because Webb has shown us that our dark matter halos are much larger than we thought, we now know that our 2 galaxies are already beginning to interact. The merging of the halos is the first step in a process that will eventually lead to the creation of a new, giant elliptical galaxy. The study of galactic dynamics, fueled by Webb's revolutionary observations, is not just a study of how we move today, but a map of where we are going in the cosmic future. One of the most intriguing aspects of these dynamics is the stellar stream phenomenon, which Webb is uniquely equipped to study in high definition. These streams are the stretched-out remnants of smaller star clusters or dwarf galaxies that have been torn apart by the Milky Way's tidal forces. As these objects are cannibalized, their stars continue to orbit the galactic center in long, thin ribbons of light that act as gravitational sensors. By observing the precise motion and wiggles within these streams, astronomers can detect the presence of invisible sub-halos of dark matter, clumps of dark matter that contain no stars at all but exert a pull on the passing stellar ribbons. Webb's ability to resolve individual stars within these distant streams provides a high-resolution map of the dark matter distribution, helping to solve the missing satellite problem, where models predict more dwarf galaxies than we can actually see. The rotation of the galaxy also influences the chemical evolution of the Milky Way, as motion dictates how heavy elements are distributed. Stars born in the inner, more crowded regions of the disk rotate and migrate outward over billions of years, a process known as radial migration. This means that the stars currently in our solar neighborhood might have originated thousands of light-years closer to the galactic center. Webb's spectroscopic instruments allow us to measure the chemical fingerprints of these moving stars, confirming that the galaxy is a dynamic, mixing bowl where stars are constantly changing their zip codes. This migration complicates our understanding of the galactic census, but provides a richer picture of how the Milky Way's mass is redistributed over eons. Furthermore, the vertical dynamics revealed by Webb have highlighted a galactic warp in the outer disk. Rather than being a perfectly flat pancake, the edges of the Milky Way are slightly curled, resembling a vinyl record that has been left in the sun too long. This warp is not static. It precesses or wobbles around the galactic center. Webb's observations of the gas and dust in the outer reaches suggest that this warp is likely a result of the ongoing gravitational tug-of-war with satellite galaxies like the Sagittarius dwarf galaxy. This discovery emphasizes that the scale of the Milky Way is influenced by its environment, constantly being shaped and reshaped by the neighbors that orbit within its massive dark matter halo. At the center of all this motion, the supermassive black hole Sagittarius A exerts its influence, but only within a relatively small sphere of influence. While it anchors the very center, it is the collective mass of the hundreds of billions of stars and the trillions of solar masses of dark matter that truly dictate the rotation of the galaxy. Webb's tracking of the S stars, stars that orbit the black hole at terrifying speeds, has confirmed the mass of Sagittarius AI to be approximately 4 million suns. However, even this monster is a minor player compared to the total gravitational potential of the galaxy, which Webb has now helped calculate with a precision that was previously impossible. Finally, the study of galactic dynamics is leading to a new understanding of galactic habitability. The way stars move through the spiral arms, passing through dense regions of star formation and potential supernovae, affects the stability of planetary systems. Our Sun's relatively circular and stable orbit within the galactic habitable zone may be a key reason why life was able to flourish on Earth. By mapping the motions of millions of stars across the disk, Webb is helping us identify other regions in the galaxy where the dynamics are stable enough to support life over billions of years. The actual scale of the Milky Way is thus not just a measure of space, but a measure of the safe havens within a swirling, moving, and often violent cosmic ocean. As we look toward the future, the motion of the Milky Way tells a story of eventual transformation. In approximately 4 billion years, our current rotational dynamics will be completely disrupted by the merger with Andromeda. The orderly spiral arms we see today will be torn apart, and the stars will be thrown into new, randomized orbits as the two galaxies settle into a massive elliptical shape. Thanks to the James Webb Space Telescope, we now have a front-row seat to the physics of this process, seeing the preview in distant colliding galaxies and applying those lessons to our own home. The motion of the stars is the pulse of the galaxy, and for the first time, we are truly beginning to understand the rhythm. The precision with which we can now measure these dynamics has led to a radical recalibration of the galactic rotation curve, a graph that plots the orbital speed of visible stars against their distance from the center. Before Webb, our data for the outermost reaches of the disk were sparse and often plagued by the obscuring effects of interstellar dust. By utilizing Webb's mid-infrared instrument, MIRI, astronomers have been able to penetrate the thickest dust lanes of the Scutum Centaurus and Perseus arms, measuring the velocities of young stellar clusters with a margin of error that has been slashed by nearly 50%. This refined data confirms that the rotation curve remains stubbornly flat out to the very limits of the detectable gas disk, providing the most robust evidence to date that the dark matter halo is not just a theoretical convenience, but a physical reality that dominates the galaxy's kinetic energy. One of the most subtle yet profound aspects of galactic motion being explored is the vertical velocity dispersion, the measurement of how fast stars move perpendicular to the galactic plane. Webb has observed that older stars in the thick disk have a much higher vertical bounce than the younger stars in the thin disk. This suggests that the galaxy has undergone significant heating events in its past, likely caused by the gravitational wakes of passing satellite galaxies, or the internal resonance of the spiral arms themselves. By quantifying this motion, Webb is helping to reconstruct a seismology of the Milky Way, using the current vibrations of the stellar disk to listen to the echoes of cosmic impacts that occurred billions of years ago. The interplay between the dark matter halo and the visible disk also creates a phenomenon known as dynamical friction. As smaller satellite galaxies, such as the Sagittarius dwarf or the Large Magellanic Cloud, plow through the invisible dark matter halo of the Milky Way, they create a gravitational wake behind them. This wake acts as a drag force, slowing the satellite down and causing its orbit to decay, eventually drawing it into the main body of our galaxy to be consumed. Webb's observations of the gas tails stripped from these falling galaxies provide a real-time look at this friction in action. This dynamic interaction is a crucial part of the Milky Way's growth scale, proving that our galaxy is a living predator that continues to grow in mass and complexity by absorbing its neighbors. Finally, the overarching motion of the Milky Way within the cosmic web must be considered. Our galaxy, along with Andromeda and dozens of smaller companions, is being pulled toward a massive gravitational anomaly known as the Great Attractor. This large-scale flow dictates the ultimate trajectory of our entire local group through the expanding universe. Webb's deep-field observations of distant galaxy clusters provide the fixed background necessary to measure our own absolute motion through space with incredible accuracy. We are moving at roughly 1.3 million miles per hour relative to the cosmic microwave background radiation, a final, staggering metric that completes our understanding of the Milky Way's place in the dynamic, moving tapestry of the cosmos. The synthesis of these movements, from the tiny, high-speed orbits of stars around Sagittarius A to the grand, sweeping motion of the dark matter halo, reveals a galaxy that is a masterpiece of equilibrium. The James Webb Space Telescope has not just given us a map, it has given us a film of a galaxy in constant, purposeful motion. The scale of the Milky Way is not a static number of miles, but a tally of the momentum, gravity, and time that bind its billions of stars into a single, rotating island of light, our cosmic neighborhood. To understand the true scale of the Milky Way, we must eventually step beyond the limits of its dark matter halo and look at the companions that share our corner of the universe. Our galaxy does not exist in a vacuum. It is the primary anchor of a bustling cosmic neighborhood known as the local group. This collection of more than 80 galaxies is a gravitationally bound system that provides the essential context for the Milky Way's size. The relationship between our galaxy and its satellite companions, and its larger peers like Andromeda, reveals that the scale of our home is defined as much by its influence on others as by its own internal structure. The most prominent members of our immediate entourage are the satellite galaxies, small collections of stars and gas that are caught in the Milky Way's massive gravitational web. The Large and Small Magellanic Clouds are the most famous of these, visible to the naked eye from the southern hemisphere as our hazy patches of light. For a long time, these were thought to be long-term residents of our neighborhood, but Webb's observations, combined with the data from the Gaia mission, suggest a more dynamic relationship. The Large Magellanic Cloud, LMC, which contains about 20 billion stars, is actually a massive intruder that is likely on its very first pass around the Milky Way. Its presence is so significant that it is actually pulling on the Milky Way's dark matter halo, causing a detectable wake that shifts the very center of mass of our galaxy. Beyond the Magellanic Clouds, the Milky Way is surrounded by dozens of dwarf galaxies, such as the Sagittarius dwarf, the Sculptor dwarf, and the Fornax dwarf. These satellite galaxies serve as test particles for measuring the extent of the Milky Way's dark matter. Webb's ability to resolve the oldest, faintest stars in these dwarf systems has allowed astronomers to calculate their orbital paths with pinpoint accuracy. The discovery that these satellites are still feeling the Milky Way's gravitational pull at distances of nearly 1 million light-years is what confirmed the revised scale of our dark matter halo. We now know that the sphere of influence of the Milky Way is far larger than the visible disk, as it effectively commands a volume of space millions of light-years in diameter. This brings us to the broader context of the local group. The local group is dominated by two giants, the Milky Way and the Andromeda Galaxy, M31. For decades, the consensus was that Andromeda was the undisputed heavyweight champion of our neighborhood, estimated to be up to twice as massive as our own galaxy. However, Webb's revolutionary observations of the galactic center and the outer halo dynamics have prompted a significant reevaluation. By accurately measuring the total mass contained within the Milky Way's 2 million light-year dark matter halo, scientists now believe the two galaxies may be much closer in mass than previously thought, or that the Milky Way might even be the more massive of the two. The scale of the local group itself is approximately 10 million light-years across. In this vast arena, the Milky Way and Andromeda act as binary anchors, drawing smaller galaxies toward them like moths to a flame. Webb has observed the Triangulum Galaxy, M33, the third largest member of the group, which is currently a satellite of Andromeda, but may eventually be influenced by the Milky Way's expanding reach. This comparative look at galactic sizes reveals that the Milky Way is a giant among galaxies. While it is dwarfed by rare, massive elliptical galaxies in the centers of distant clusters, it is larger and more complex than 90% of the galaxies in the known universe. Webb's comparative studies have also looked at distant Milky Way twins, galaxies that share our spiral structure and mass but exist in different environments. By comparing our galaxy to these distant peers, Webb has revealed that our cosmic neighborhood is relatively quiet. We are not currently undergoing the violent mergers seen in the Stephan's Quintet cluster, which has allowed our spiral arms to remain stable and well-defined for billions of years. This stability is a key component of the Milky Way's scale, allowing it to grow systematically rather than through chaotic, destructive collisions that would have stripped away its delicate, star-forming gas. One of the most fascinating revelations regarding our neighborhood is the merging of the halos. As Webb has shown, the dark matter halos of the Milky Way and Andromeda extend so far that they are already nearly touching. In the space between these two giants lies a bridge of hot, ionized gas, known as the warm-hot intergalactic medium. Webb's spectroscopy has detected signatures of this gas, which represents the missing matter that exists outside of galaxies, but within the local gravitational system. This discovery implies that the Milky Way is not an island, but is part of a continuous structure of matter that connects us to Andromeda. The future of our cosmic neighborhood is one of unification. In about 4 billion years, the local group's two largest residents will merge. This process, which Webb is helping us model by observing other merging pairs across the cosmos, will create a massive elliptical galaxy nicknamed Milkomeda. The scale of this future entity will be even more staggering, as it will consolidate the hundreds of billions of stars and the trillions of solar masses of dark matter from both galaxies into a single cohesive system. Our current neighborhood is merely a snapshot in a long history of assembly that will eventually lead to a much larger, singular galactic home. Ultimately, looking at the Milky Way within its neighborhood reminds us of the humility of our position. We live on a small planet, orbiting an ordinary star, in a massive galaxy that is itself just one of two major players in a small group of galaxies. Yet, through the eyes of the James Webb Space Telescope, we have developed the capability to map this neighborhood, to weigh the invisible dark matter that binds us, and to understand the true scale of our place in the universe. The Milky Way is a titan of the local group, a sprawling, magnificent structure that continues to reveal its secrets one light year at a time. A critical component of this neighborhood census is the relationship between the Milky Way and its smaller satellite galaxies, which act as a laboratory for studying the missing satellite problem. Standard cosmological models once predicted that the Milky Way should be surrounded by hundreds of dwarf galaxies. Yet, until recently, we could only detect a few dozen. Webb's specialized instrumentation has helped bridge this gap by revealing ultra-faint dwarf galaxies, collections of stars so sparse and dim that they were previously indistinguishable from the background noise of the universe. These tiny companions, often containing only a few thousand stars, are held together by a disproportionately massive amount of dark matter. By mapping their orbits, Webb has shown that these satellites are not just random passers-by, but are deeply embedded in the sub-halos of our galaxy's 2 million light-year dark matter envelope. To further visualize the scale of our neighborhood, we must compare the Milky Way to other galactic structures found within the local group and beyond. While the Milky Way is a giant among its immediate peers, it is categorized as a barred spiral galaxy, a type that is relatively common but varies wildly in scale. When placed side by side with the Triangulum galaxy, M33, our neighbor is revealed to be significantly smaller, with only about 40 billion stars compared to our estimated 100 to 400 billion. However, when we look further out at the M87 galaxy in the Virgo cluster, the Milky Way suddenly seems modest. M87 is a supergiant elliptical galaxy, with trillions of stars and a black hole that is over 1,000 times more massive than Sagittarius A. Ars. This comparative scale helps astronomers understand that while the Milky Way is a heavyweight in its local cosmic corner, it is part of a much larger hierarchical universe, where size is often determined by the environment and the history of galactic mergers. Webb's observations have also highlighted the importance of the Magellanic Stream, a massive river of gas stripped from the large and small Magellanic Clouds as they fall toward the Milky Way. This stream stretches across a significant portion of the southern sky and contains enough gas to trigger a new wave of star formation in the Milky Way's disk for the next billion years. The existence of such a structure demonstrates that our neighborhood is a messy, interactive place where material is constantly being exchanged. The scale of the Milky Way is therefore not just a measurement of where our stars end, but where our gravitational influence over the Magellanic Stream and other neighbors begins. This neighborhood interaction also plays a role in the galactic habitable zone. By studying how our neighbors interact with us, Webb helps scientists understand if the Milky Way's position in the local group makes it a uniquely stable environment for life. A more chaotic neighborhood, filled with frequent major mergers, might have subjected our solar system to intense radiation or gravitational disruptions that could have prevented the long-term evolution of life on Earth. The quiet, systematic growth of the Milky Way, confirmed by Webb's observations of our distant analogs, suggests that our neighborhood is a rare oasis of stability. As we conclude this survey of our cosmic neighborhood, we are left with a picture of the Milky Way as a titan that is inextricably linked to its surroundings. From the tiny dwarf galaxies that act as its gravitational sensors to the looming presence of Andromeda, every member of the local group helps define the actual scale of our home. The James Webb Space Telescope has not only measured the distances between these objects, but has also revealed the invisible threads of dark matter and gas that bind them together. We now know that to truly measure the Milky Way, one must measure the entire local group, for our galaxy's story is a shared history of motion, mass, and the eternal dance of the cosmos, implications, and future. The revelations brought forth by the James Webb Space Telescope regarding the Milky Way's actual scale do more than just update our measurements. They fundamentally alter our understanding of the life cycle of galaxies. By proving that a galaxy like our own could achieve such a massive dark matter halo, reaching nearly 2 million light-years in diameter while maintaining a highly organized spiral structure, Webb has forced cosmologists to rethink the timeline of maturity for the universe. It appears that the blueprints for cosmic giants were laid down much earlier than previously thought, with the seeds of the Milky Way's current scale already germinating just a few 100 million years after the Big Bang. This shift in understanding has profound implications for our models of galaxy formation. We once believed that a galaxy's size was a slow accumulation of random accidents, a messy history of chaotic mergers. However, Webb's observations of early universe analogs like firefly sparkle suggest a more systematic and guided growth. This implies that dark matter is not just a passive glue holding stars together, but an active architect that dictated the scale and structure of the Milky Way from its very inception. The realization that our galaxy is nearly touching Andromeda's halo today means that the local group is less a collection of separate entities and more a singular, evolving gravitational tapestry. Looking ahead, these discoveries have opened a new frontier of mysteries that future observations will need to solve. While we have mapped the extent of the dark matter halo, we still do not know what the dark matter itself is composed of. Webb has provided the where and the how much, But the what remains the ultimate prize of modern physics. Future missions will likely use Webb's data as a foundation to look for subtle lensing effects within our own halo. Tiny distortions in the light of distant galaxies caused by clumps of dark matter, to finally see the internal structure of this invisible cocoon. Furthermore, the discovery of the hot gas halo, which contains mass nearly equal to all the stars in the galaxy, raises questions about how this reservoir of material will fuel the Milky Way's future. There is also the mystery of the galactic heartbeat. Webb's observation of the near-constant flickering and flares of Sagittarius AI suggests that our central black hole is far more active than its quiet reputation implied. Future long-term monitoring will aim to determine if these daily flares are a sign of a looming active phase for the Milky Way. If the black hole were to begin consuming material at a higher rate, the resulting radiation could fundamentally change the environment of the inner galaxy, potentially affecting the habitability of systems much closer to the center than our own. Beyond the physics of individual stars, the scale of discovery forces us to consider the long-term evolution of the baryonic cycle within the Milky Way. The presence of massive amounts of hot gas extending hundreds of thousands of light-years suggests that the Milky Way has a significant savings account of matter for future star formation. As the dark matter halo continues to pull in satellite galaxies like the Magellanic Clouds, this gas reservoir will likely be enriched and compressed, leading to a vibrant future for our galaxy that stretches far beyond the current age of the universe. One of the most significant implications of Webb's findings is the refinement of our cosmic distance ladder. By observing Milky Way-like galaxies in their infancy, Webb has provided a way to calibrate the distance and mass of more distant objects. This doesn't just help us understand our own home, it helps us understand the expansion of the universe itself. The specific discoveries in Sagittarius C and the central black hole provide a local laboratory for testing the laws of physics under extreme conditions, allowing us to project that knowledge onto the most distant quasars and active galactic nuclei in the cosmos. The future of galactic exploration will also focus on the galactic warp and the three-dimensional structure of the dark matter halo. While we now have a diameter of 2 million light-years, the exact shape, whether it is a perfect sphere, an elongated football, or a flattened disk, will tell us about the history of the Milky Way's past encounters with other giants. By observing how distant globular clusters and satellite galaxies orbit within this halo, Webb and future telescopes will be able to weigh the dark matter in different sectors of the galaxy, providing a map of the invisible scaffolding that supports our existence. Finally, these revelations lead us back to our own place in this newly understood cosmic home. We now know that we live in a galaxy that is far more magnificent, expansive, and ancient than the simple band of light seen by our ancestors. We are part of a structure that stretches across millions of light years, bound to our neighbors by invisible threads of gravity and destiny. Understanding the actual scale of the Milky Way provides a sense of perspective that is both humbling and empowering. We are small, yes, a single planet in the suburbs of a giant, but we are also the eyes of that giant, capable of building tools like Webb to look back at our own origin and forward to our ultimate merger with the cosmos. As we look to the night sky, we no longer see just a hazy river of light. We see the visible edge of a 2 million light-year titan that is still growing, still breathing, and still surprising us. The James Webb Space Telescope has not just rewritten our textbooks, it has expanded our horizons, proving that the scale of our curiosity is the only thing capable of matching the scale of the universe itself. The journey through the Milky Way's actual scale is far from over. In many ways, Webb has shown us that our exploration has only just begun. The implications for future generations of astronomers are clear. We must stop thinking of the Milky Way as an isolated island. Instead, we must view it as a primary node in a cosmic network of mass and energy. The data being collected today will serve as the foundation for the galactic archaeology of tomorrow, allowing us to trace the movement of every star back to its birthplace and predict the collision with Andromeda with second-to-second accuracy. Webb has given us the tools to not only see where we are, but to understand how we came to be, and where our cosmic home is headed in the eons to come. This expanded view of our galaxy also changes the search for life. By identifying star-forming regions that operate under different rules, Webb is showing us where the next generations of planetary systems are being born. The actual scale includes these millions of potential new homes, extending our search for intelligence and habitability far beyond our local neighborhood. We are part of a massive, ongoing story of creation, a story that is millions of light years long and billions of years deep. As we conclude this journey, remember that the numbers, the 2 million light years, the 400 billion stars, the 4 million solar mass black hole, are more than just statistics. They are a measure of the majesty of the universe and our capacity to witness it. The Milky Way is our home, and for the first time in human history, we are beginning to see just how grand that home really is. Beyond the immediate physical measurements, the data from the James Webb Space Telescope, JWST, is forcing a radical rewrite of how we understand the metabolism of galaxy formation. Traditionally, astronomers believed that galaxies like our own required billions of years of slow, chaotic interactions to build up heavy elements and settle into an organized shape. However, Webb has observed cosmic adolescence, young galaxies just 12.5 billion light-years away, that have already matured at a rate that mimics 2-year-old children acting like teenagers. These early galaxies are already rich in metals like carbon and oxygen, and, most surprisingly, many already possess rotating stellar disks similar to the Milky Way's spiral structure. This accelerated timeline suggests that the Milky Way's early evolution was not a series of random accidents, but a highly efficient process driven by the immense dark matter structures Webb is just beginning to map. The discovery of thick and chaotic disks in galaxies as far back as 10 billion years ago suggests a two-step formation process. Galaxies first built a turbulent, thick disk before settling into the calm, thin disks we inhabit today. For a galaxy of our size, this orderly transition likely began about 8 billion years ago, providing a much-needed baseline to determine if our own formation was a cosmic typicality or a rare exception. These observations have also opened the door to several new cosmic puzzles that defy current scientific models. Among the most fascinating are blue monsters, ultra-compact but extremely bright galaxies, and little red dots, highly compact sources from the cosmic dawn that appear far more mature than they should be for their age. Some researchers are now proposing exotic explanations for these anomalies, such as the existence of dark stars, powered by dark matter annihilation rather than nuclear fusion. If confirmed, these dark stars could be the missing link, that explains how supermassive black holes at the heart of galaxies grew so large so quickly. The future of galactic exploration will focus heavily on galactic archaeology, using Webb's infrared precision to peer through the dust of our own center to find the fossil records of these early stages. By studying the specific chemical markers of polycyclic aromatic hydrocarbons, PAIs, and crystalline silicates, Webb is helping us trace the cosmic highway that transports the building blocks of planets and life from the hottest parts of star-forming disks to the outer edges of new solar systems. This research doesn't just teach us about the Milky Way, it teaches us how the universe itself became transparent to light and hospitable to complex matter. As for our long-term destiny, the fabled collision with the Andromeda Galaxy is now far less certain than it was just a few years ago. New simulations incorporating the latest data from Hubble, Gaia, and now Webb suggest that there is only a 50-50 chance of a direct merger within the next 10 billion years. The orbit of the Large Magellanic Cloud appears to be exerting a perpendicular pull that could cause the two giants to simply fly past each other, separated by hundreds of thousands of light years. While a merger would eventually create Milkomeda, we now understand that our two galaxies might continue their orbital waltz for far longer than we ever imagined. Ultimately, our place in this newly understood cosmic home is one of unprecedented clarity but growing mystery. We now know we live in a galaxy that grew faster, holds onto its matter more tightly through dark matter filaments, and is part of a local neighborhood that is far more stable than the chaotic clusters of the early universe. The James Webb Space Telescope has not just given us a better telescope. It has initiated a real revolution in our understanding of the universe's most fundamental objects. We are no longer just observers of the dark. We are the chroniclers of a living, breathing history that stretches from the first dark stars to the potential merger of worlds billions of years from now. Closing meditation. Now, take a deep, slow breath and let the weight of these vast cosmic revelations settle gently within you. As you find that perfectly comfortable position once more, feel the tension finally leaving your body, like light fading at the edge of a distant galaxy. The scale of the Milky Way is no longer a collection of daunting numbers or staggering distances. It is a peaceful, protective cradle that holds everything you have ever known. James Webb has given us a new way of seeing, but tonight, let that vision become a soft blanket of stars. Imagine yourself drifting through the silent, velvet dark of our galactic home, a home that extends far beyond the horizon, reaching out with invisible arms of dark matter to touch the neighbor galaxies. You are part of an enormous, invisible cocoon, a structure so grand that it defies the worries of a single day. In this magnificent architecture, the time it takes for light to travel is not a barrier, but a testament to the endurance of the universe. As light journeys for millions of years to cross our halo, let your mind journey into a state of deep, undisturbed rest. Picture the hazy band of the Milky Way as a gentle, flowing river of light, carrying the stories of billions of stars through the ages. Feel the slow, rhythmic rotation of our galaxy, a pulse that has beaten for billions of years and will continue for billions more. You are anchored by the same gravity that holds the great spiral arms together, safe and secure in the galactic suburbs, protected by the vastness of space. There is a profound peace in realizing that while we are small, we are never truly lost. We are an essential part of a beautifully ordered and remarkably ancient story. let the 2 million light-year expanse of our home become a space of infinite quiet. The entire history of humanity, every tool ever made, and every word ever spoken, is just a fleeting moment in the life of the stars. As your thoughts drift like cosmic dust, know that you are right where you belong, in a universe that continues to surprise and sustain us. Close your eyes now, merging your scientific curiosity with a peaceful contemplation that allows you to fully unwind. Breathe, relax, and drift into the soft, starlit embrace of the cosmos. Good night.